So now we're going to actually use, now we're actually going to use these identities to help us do things, right? One of the things that we can do is, one of the ways that we can use these trigonometric identities, or what it allows us to do, is write trig functions in terms of other trig functions. So there'll be times where I'm going to need to simplify expressions, or for me to do things or solve an equation, I'm going to have to rewrite my trig function as in terms of other trig functions in order for things to work out nicely. And these identities help us do that. We can also simplify trig expressions written with more than one trig function. More than one trig function. And again, that helps us with solving things or making things look a little bit better. And we can evaluate all other trig functions. When the value of one trig function is known. And so, for instance, if I know sine of theta, of some angle theta, then I can figure out what the other values of trig functions will be. The values of the other trig functions at that angle would be. All right, let's look at each of these types of things that we can do now that we know some other trigonometric identities. For example, example 2. It says simplify the expression 1 plus cosine of beta times 1 minus cotangent beta times sine beta. Okay, and so for me to simplify this equation, or this expression, this is not an equation, this expression is, only thing I can do is, I could try to multiply, but what you're going to have to start doing is kind of taking a step back and trying to see if you see any identities that you can use. And one of the places where I can see an identity is right here with this cotangent function, especially since it's multiplied by a sine, right? We know from our quotient identity that cotangent is the exact same thing as cosine beta over sine of beta. All right? And I still have that other sign there. And so what this allows us to do is cancel the sine of betas. And so this second expression is nothing more than saying 1 minus cosine beta. And now that looks a lot nicer. It got simpler by rewriting that cotangent as a cosine over sine. Now we want to simplify it further. Notice that we have a difference of squares. What a difference of squares would get factored into, right? You can go through the full method, or you can remember that when you have a plus b times a minus b, it is the same thing as a squared, or 1 squared, which is 1, minus b squared, that would be cosine squared of beta. Okay? And so now this actually looks a lot simpler. Now I have a 2 as my exponent, but it is an expression. It's not a product of expressions. And then I can think about my Pythagorean identity. Now this is something that you will want to get used to. For instance, my sine squared of theta plus cosine squared of theta, I know that that equals 1. Now, if you note here, this is written as a 1 minus a cosine squared of beta, right? Since I have a 1, a sine squared, and a cosine squared here, I could write this. If I subtract cosine squared of theta from both sides, I'd see that sine squared of theta is the same thing as 1 minus cosine squared of theta. And so this expression here is the exact same thing as sine squared of theta. So it's like me using my Pythagorean identity, but writing it in a form that I can make it useful for an expression that I can see, which is that expression there. All right, and so you can always rearrange your Pythagorean identities or any of your identities so that you can get what you need. For instance, if I were to look at my cotangent beta, well, that's neither here nor there. I'm sorry. All right, let's go to another example. Here, it says use identities to find the exact value of alpha for the remaining trig functions if secant of alpha equals negative 4 square root of 5 over 5, and my angle is going to be between pi over 2 and pi, okay? So I get that secant of alpha equals negative 4 square root of 5 over 5, right? I want to find sine alpha, cosine alpha, tangent alpha, cosecant alpha. I already know secant alpha. And I want to know cotangent of alpha. Okay? Well, I'm going to use identities. I know for a fact that secant and cosine are reciprocals of each other, right? And so if I know the secant, I can do cosine of alpha by doing the reciprocal of my secant. Well, that's just flipping the fraction, right? And of course, I want to rationalize my denominator, so I'm going to multiply the denominator and the numerator by the square root of 5. I'm going to get negative 5 square root of 5 over, well, this times that, the square root of 5 times square root of 5 is square root of 25 or 5, and I multiply that by 4, I get a 20. And notice here, 5 over 20 is, 5 goes into 20 evenly 4 times, and so this actually equals negative square root of 5 over 4. Okay, so cosine of alpha equals negative square root of 5 over 4. So I've got this one. Okay, now I need to find some others. And there's multiple ways that you can do this. This is what I'm going to do. I'm going to find sine next. Since I have cosine, I'm going to find sine because I know that sine squared of alpha plus cosine squared of alpha equals 1. If I want to find sine, I'm going to put my value of cosine in there, and I'm going to square it, and that's going to go into place of cosine squared alpha. All right, that means that sine squared of alpha equals, well, negative times negative is a positive. Square root of 5 squared is 5, and 4 squared is 16. Okay, and so if I want to, that is not an equal there. Haha. I was jumping the gun there. So let's go back. That'll be plus 5 over 16 equals 1. I want to solve this equation for sine. I'm going to isolate the sine squared term. That'll be a 1 minus 5 over square root of 16. If I continue to simplify that, I'm going to get, that'll be 16 over 16 minus 5 over 16, or we would say 11 over 16. I take the square root of both sides, and I get sine of alpha equals plus or minus square root of 11, and the square root of 16 is 4, so I'm going to go ahead and do that. Now, for me to determine whether this is going to be a plus or minus, remember, this is still a variable expression, so you remember when you take the square root of a variable expression, it's actually the absolute value of sine of alpha. We don't write its absolute value, or another way to go around that is to just put plus or minus on the other side, and so we get plus or minus square root of 11 over 4. Now, I'm going to determine whether I'm going to use a plus or minus by looking at whether my sine of this angle will be positive or negative in whatever quadrant I have highlighted here. Since I have from pi over 2 to pi, that's in the second quadrant, and sine is positive in the second quadrant, so sine equals square root of 11 over 4. Okay? Once I know my sine function, I know my cosecant function, or I can find it by doing the reciprocal. Okay? Because cosecant, using that reciprocal identity, is 1 over the sine of alpha, right? And so since I know that sine of alpha is the square root of 11 over 4, same thing as doing 4 over the square root of 11. If I rationalize my denominator, I get 4 square roots of 11 over 11. And so I have cosecant of theta as that. So I know sine, cosecant, cosine, and secant. Now I'm going to find my tangent and my cotangent. All right. Now you can use other identities, but I'm going to use the quotient identity to tell me, or to figure out that tangent can be written as sine over cosine, right? And I already know my sine. Sine is square root of 11 over 4, and my cosine is negative square root of 5 over 4. And so if I simplify that, I multiply by the reciprocal of that denominator. And so I get negative square root of 11 over the square root of 5. I rationalize my denominator. I get negative square root of 55 over 5, okay? And then now that I know my tangent, I can find my cotangent by doing 1 over my tangent of alpha. So that would be a negative 5 over the square root of 55. And so I get negative 5 square root of 55 over 55. If I want to simplify that, 5 goes into 55 11 times, so I get negative square root of 55 over 11. And that is how I can use one trig function and my identities to help me get my other trig functions.